Okay, this is one issue that we have to address seriously and in explicit detail. Because in this video, you see a little Geo Metro. I can't draw a Geo Metro. You see a little Geo Metro. You want to see a little Geo Metro bigger? Okay. I see a little Geo Metro bigger. You see the Geo Metro, and in this fuel tank, in the Geo Metro, this is the regular fuel tank, and over here, lengthwise, we got the hydrogen tank. In this tank, on the video, you'll see we put gasoline, we can put diesel, we can put terpenes, we can put alcohol, we can put poor quality alcohol, we can put in poor quality gasoline, because what we're doing is we're adding from the hydrogen tank a little bit of hydrogen with this fuel into the engine. Now, the rule of thumb, and this is a very accurate rule of thumb, is when you're doing this, 5% to 7% of the energy going into the engine must be hydrogen. So if we're putting 100 BTUs of gasoline into the engine through the normal process, to high boost it and make its combustion be dominated by hydrogen. Remember we were talking about how slow gasoline, when ignited, can burn, and it has to burn like this, and it'll cover the cylinder walls in here. Well, when you put hydrogen in, basically it turns that slow combustion to bang. Okay? That's an abstraction, but the hydrogen is going to burn 8 to 10 times faster than the gasoline. So we're looking at about 40,000 feet per second flame speed in the engine versus 5 to 6,000 feet per second gasoline. So it burns a lot quicker. Now, I've made an analogy before to this. This is like taking a room, and let's say you put a bunch of wood into it, okay? And really good dry wood that wants to burn, and you throw a match into it. It's going to start burning here slowly, slowly, and work its way out. If you took that same room full of wood and you poured it full of gasoline and you threw that match in, what would happen? You're right. Foomp. Okay? It would burn, it would start everything going very quickly. And the wood would burn, and the room would be on fire, and the house would burn down. Same thing as the hydrogen going into the cylinder full of gasoline. Think of the gasoline as the wood and the hydrogen as gasoline. The hydrogen combustion dominates the gasoline combustion. Same thing here. The gasoline combustion dominates the wood combustion. So the rule of thumb is you need 5 to 7% of your BTUs going in to be hydrogen into the cylinder for this to happen. It really starts around 5%. You need a minimum of 5%. Now there are people selling hokey, BS, worthless, good-for-nothing pieces of junk and getting your money based upon your ignorance of the subject. Of little electrolyzers that go under the hood of your car and hook up to your alternator, and they say, it's going to improve your fuel economy. And they might be a piece of PVC pipe, and they might have some iron plates into it. And into here you might put some caustic soda, sodium hydroxide, drain cleaner and water, or it might be baking soda and water, and you hook up 12 volts and ground to this, and it's going to bubble hydrogen and oxygen ever so slowly out of here. And you're going to use this hydrogen to go into the air intake and the oxygen into the air intake, and it's going to improve your fuel economy. Absolute 100% BS. Does not work, will not work. I don't care what their numbers are. I don't care what they're telling you. They're wrong. Their numbers are wrong, and their measurements are wrong. They might believe it's valid. They might honestly believe it's valid, but it's not. How do I know? Well, one, I know a great deal about hydrogen, vehicles, fuel cells, internal combustion fundamentals, and I was also a development engineer for 10 years in the scientific labs of Chrysler Corporation, doing nothing but vehicle development work. I know vehicles from bumper to bumper, thermally, chemically, you name it. Done a lot of work with them. Now, if you think that makes me part of the automobile conspiracy, and I'm telling you this to deceive you, then shut up and go away. Turn the thing off and go bang your head against a piece of concrete, because you'll be doing all of us a favor. I am a scientist. I'm giving you the best science in the world, and you're ready? Here it comes. I'm going to show you exactly mathematically why it doesn't work. And I'm going to try to show you in a way that even if you didn't finish your algebra, you'll understand. Because, you know, if I can't explain it to someone, I'm worthless. So I'm going to give it my best. I'm going to try. Let's say you have a vehicle that gets, we're going to be really nice, okay? I'm going to use good, I'm going to give it every benefit of the doubt. You got a vehicle that gets 40 miles per gallon, okay? Like one of these little Toyotas. Let me tell you, if you get a vehicle getting 40 miles a gallon and you want to try to save money by putting hydrogen in it, don't, okay? You're doing good right here. If you want to put hydrogen in it because you want to learn, you enjoy it, you like the chemistry, you like the physics, you think there's economics in it, you want to be a part of it, you're excited about it, then do it, okay? Do it. You're getting 40 miles per gallon, put the gasoline in and be happy. So you get 40 miles a gallon. Now let's say you are driving 60 miles per hour. Yeah, I know, okay, let's say you slow down, you're driving 60 miles per hour. And you're driving 60 miles per hour for 1 hour. What does this mean? If you're driving 60 miles per hour for 1 hour, this is our unit of time here. This is our time rate, and this is our fuel consumption. That means you have used 1.5 gallons of gasoline. Okay? And what this is, it's 60 miles per gallon divided by 40 miles per gallon equals 1.5. So 1.5 gallons of gasoline. Now do not forget what I told you back here, that we need 5% to 7% of our BTU value going into the engine to be hydrogen. So here we're using 1.5 gallons of gas. Now, how do we know what is what's 5 to 7%? Okay, gasoline has approximately, even numbers here, 120,000 BTUs per gallon. This is an amount of energy, okay? You can think of it as tennis balls. You can think of any unit you want. This is a unit of energy. Well, I'll give you a quick side. What is 1 BTU of energy? If you have 1 pound of water and you want to heat it 1 degree Fahrenheit, you want to raise it from 68 degrees Fahrenheit to 69 degrees Fahrenheit, or you want to raise it from 150 degrees Fahrenheit to 151 degrees Fahrenheit, or you want to raise it from 33 degrees Fahrenheit to 34 degrees Fahrenheit. Get the picture? It takes 1 BTU of energy to do that. To give you an idea, there are 8.3 pounds in 1 gallon of water. So to raise 1 gallon of water, 1 degree F, it would take 8.3 BTUs. Now, okay? And you're going, holy cow, 1 gallon of gasoline at 100% efficiency can raise, that's a lot of water, a lot of temperature. Yeah, it is. There's a lot of energy in 1 gallon of gasoline. There is a lot of energy in 1 gallon of gasoline. Let me repeat that. There's even more in a gallon of diesel. So anyways, you got 120,000 BTUs. Now, if I need to have 5 to 7% of this, now we're going to be generous, we're going to use 5%, the lower number. So, I'm going to take 120,000 BTUs multiplied by 0.05, which is 5%. Look, I have my idiot machine here. 120,000 times 0.05 is 6,000. So, I'm going to put in 120,000, I'll move over here for you, BTU, gas, and I'm going to put in 6,000 BTUs of hydrogen. Oops, sorry, got ahead of myself. 6,000 BTUs of hydrogen. Doesn't sound like much, right? Okay. Now, remember, we're supposedly making this 6,000 BTUs of hydrogen by electrolysis underneath the hood from the alternator. Let me refer to my notes here. Okay, so we got, oops, I goofed. What did I do wrong? Did you see it? Did you see it? Yeah. I have 1.5 gallons of gasoline times 120,000 BTUs per gallon. Okay? That equals 180,000 BTUs being used. And I need 5% of that. So 0.05 times 180,000. I need to make 9,000 BTUs H2. I know you're screaming at the camera that I can't do my math. I caught it. Here it is. So, backing up. 40 miles per gallon, 60 miles an hour for 1 hour is 1.5 gallons of gasoline used. There are 120,000 BTUs of energy, higher heating value, in 1 gallon of gasoline. So if I have 120,000 BTUs in 1 gallon, I use the gallon and a half. 1.5 times 120 is 180,000 BTUs in gasoline. I need 5% of it to be hydrogen times 0.05. I need 9,000 BTUs of hydrogen to be made by my little electrolyzer under hood on my alternator as I'm driving the vehicle. Next page. So, 9,000 BTUs. What does that mean in terms of voltage in amps? Be careful, people who go amps. How much voltage and amperes do we need? Current. So we want 9,000 BTUs of H2. Now, I bet you didn't know that there are 3,412 BTUs in 1 kilowatt hour. You're going to wonder why I said we were running the car for 1 hour. That's my unit of time. So there's 3,412 BTUs in the production of 1 kilowatt for an entire hour. So we need 9,000 BTUs of hydrogen to be made in 1 hour because I'm driving at 60 miles per hour for 1 hour. So this is simple math that even I won't goof up. 9,000 divided by 3412. This is going to be 2.63 kilowatt hours of power. Now in Europe, they rate their engines in kilowatts. Okay? In America, we rate our engines in horsepower. So kilowatts is generally referred to in the United States as a rate of electric energy and horsepower as a rate of shaft horsepower mechanical. But you can swap them back and forth. So there's 2.36 kilowatt hours. Well, kilowatt, okay, that's the same as 1,000. 2.63 kWh equals 2,630 watt hours. Got it? This is kilo, 1,000. There's no kilo here. So you multiply 2.63 times 1,000, which is this kilo, you get that. Sorry if I'm boring some of you, but I have to explain it to people as if they're not familiar with this. Besides, it's a good refresher. So we need 2,630 watts over an entire hour. Well, what is watts? Watts equals volts times amps. What is our voltage in the vehicle? Our voltage, we're going to be generous again for this electrolyzer. We're going to say we're running at 13.8 volts, which is the voltage, one of the ideal charging voltages you'll get coming out of the alternator. It could range up to 14.2, but 13.8 is a norm. So 2,630 divided by 13.8. Exactly here. Watts divided by volts equals amps. So 2,630, fingers don't work, 2,630 divided by 13.8. Holy cow, I need 190 amps coming out of my alternator. Does that seem like a lot to you? Let's put it this way. Your standard alternator in a large sport utility vehicle running at maximum output, which would be about 8 to 10,000 RPMs on the alternator. It's a multiplication. The engine might be running at 5,000 RPM. But the alternator is sitting up here, and it's on a smaller pulley, and this is on a bigger pulley, so you have a speed advantage. So this alternator needs to run at wide out, as fast as it can go. A typical alternator on a large sport utility with your heated seats, 2 blowers, front and rear for the air conditioning and heating, electric fans, headlights, wipers, a car stereo going thump, 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 about as worthless as the exhaust resonator. It'll output about 120 amps. That's it. You need 190. And this is not for a sport utility vehicle getting 20 miles to the gallon. You need 190 amps for this little yip-yip Toyota vehicle getting 40 miles per gallon. If this was a sport ute going 20 miles per gallon, I'd be using twice the amount of fuel. 60 divided by 20 instead of 60 divided by 40. This is 1.5. 60 divided by 20 would be 3. You double everything. So if this was a large sport utility vehicle, I would need 380 amps at 20 miles per gallon to get 5% H2 into the intake by BTU value. But, you know, again, saying this was a 40 mile per gallon, you need 120 amps out of the alternator, and so you're only getting 120, you need 190. You can't make the 5%. Now, plus each headlight takes about 8 amps, for 16. Where's that energy coming from? Your front blower for your AC or your heater core, and that's a good 25 amps on high. Windshield wipers, another 8 amps. Your EBL. You know what an EBL is? Electric backlight. In other words, rear window defogger. It's a little automotive term for you. There's a 15 amps right there. And gee, where are you going to get all this other current if you're using all your 120 amps, trying to make up the 190 to give you the 5% of energy to put into the engine? Well, you don't have it. You're not going to get it. And it gets even worse. Not only are you not going to get it, it is going to be seriously counterproductive even if you were to, yeah. This is 190 amps here to make that amount of hydrogen. You want to know what makes this worse? Okay, 190 amperes. They're showing you how to do it with this little electrolyzer in a PVC tube, metal tube, whatever. And it's got plates in it. And it's a homemade type of thing. Here's your wires going in. And you're putting 12 volts across here and ground here. And you're making your hydrogen gas. Now, really good electrolyzers, commercial electrolyzers, okay? On a good day, they are 60% efficient. There's some real rocket science ones out there that do 90 plus, but those are so expensive at the moment only NASA can do them. So 60% is a good electrolyzer number. And you know how that's done? The theoretical voltage across the cell needed for doing electrolysis is about 1.4 volts. But you figure with losses and some stuff, they're going to run about 2.0 volts. So what you need is 1, 2, 3, 4, 5. You need 6 cells with 12 volts all the way across here. Okay? That begins to start to make a decent electrolyzer. Now, these plates in here that we talk about, you can't put your finger in these. You're putting your finger in the middle of them and everything else. World-class electrolyzers that are manufactured today, you have one plate, and generally this plate has a lot higher surface area on it. It might be porous, have a whole bunch of holes in it. It might be grooved. It might have a bunch of fibers on it. High surface area, not a flat piece of metal. And there's another plate right here. And then there's a separation membrane in here. So the H2 goes this way and the O2 goes this way. Okay? You see the separation membrane in here? You know how thick that is in a good electrolyzer? This thick right here. As thick as a sheet of paper. The closer these plates are, the more efficient you get. The further the plates are apart, the less efficient you get. So, let's say you had one of these under your hood, and of course you still don't have enough amperage to go through the thing. Let's say you did, and you're at 60% efficient. You know how efficient this thing is? 10%. On a good day. World class, this would be 60% with this type of plates in here. And of course, this would be taking up more room underneath your hood than half your engine. So 60%, and you need 190 amps. So 190 divided by 0.6. 190 divided by 0.6 is 316 amps. 316 amps that you need, that you don't have, because you only have 120. Well, okay, Charlie, I can hear you yelling at me. What are you going to do? Well, I am going to take my internal combustion engine. You say, okay? And I'm not going to have one alternator up here. I'm going to have another alternator here, and I'm going to have another alternator here, and I'm going to have another alternator here. I am going to run you run the belt like this in case you want to do it. I'm going to run me 4 alternators or 5 alternators. I'm going to make me all them there amperes that I need to run that there electrolyzer. I'm sorry, I've been down in the South too much. I'm a Michigan person transplanted down into Texas and Arizona. I'm speaking like that again. Transplanted down into Texas and Arizona. So let's say you were going to make that. Oh gee, shall we be really generous again? Let's use the 60% number rather than the 10% number. Just like we were being really generous and we're using 40 miles per gallon instead of 20 miles per gallon. Let's be generous, okay? So we're going to use 60% efficiency, and let's round this up. Say we need 320 amps. Again, this is the amount of current and voltage we need. We're at 13.8 volts. Running into an electrolyzer that somehow you made 60% efficient. We need 320 amps to make the 5% H2 to go in to feed with the gasoline into the engine, air intake, on a vehicle that's getting 40 miles per gallon, going 60 miles per hour for 1 hour. Okay? So, 5% H2. In case you're wondering, I got all my notes here. I did this before I did this. So, we need 320 amperes. Okay, well, how are we going to get 320 amps? Well, over here you have the output shaft of the engine. This is connected directly to the crank, which we explained earlier back here in the 4-cycle demonstration. Is exactly where the piston connects to the crankshaft. This turns the shaft out here, which has a serpentine belt on it, which is going to turn your alternator, your alternator, your alternator, your alternator. It's going to turn your water pump. It's going to turn your AC compressor. It's going to turn your power steering pump and anything else that we're putting on the front of the engine these days. So, you got 320 amperes needed here. So how are we going to make this? Well, our 320 amperes. Well, let's go backwards now with our numbers the way we came, now that we factored in our electrolysis inefficiency. 13.8 volts multiplied by 320 amps. We need 13.8 times 320. We need to make, we're going to round the numbers off, 4,400. That's 4,400 watts. And that is, well, you want to know what that is? Let's do a little number here first. Let's put this into a number you can relate to. 4,400 watts. Well, there are 746 watts in 1 horsepower. In this case, it's going to be 746 watt hours in 1 horsepower hour, because we're running for an hour. So 4,400 divided by 746. This means it's going to take 5.89, let's say. It's going to take 5.9 horsepower off of this shaft, turning these alternators to make that 320 amps. Well, you go 500, well, 5.9 horsepower. Well, you know what? On a good day, this alternator and this pulley system turning it, belt slippage and everything else, is going to be about 50% efficient on a good day. But let's give these numbers the benefit of the doubt, and let's say we're using world-class alternators, super gripping belts, and let's say we are 75% efficient. So 5.9 divided by 0.75, this is going to be 7.86, so let's say 7.9 horsepower. It is going to take 7.9 horsepower from this shaft right here to make that 320 amps if we're 75% efficient, and we're not, to make the 5% H2 through a 60% efficient electrolyzer that we don't have, to make the 5% BTU hydrogen to go into the engine with the gasoline that we're burning. Well, 7.9 horsepower, you think that's not much. You know what? In this little Yip Yip vehicle, getting 40 miles per gallon, on a good day, a really good day, you know how much energy it would take to move this vehicle down the road at 60 miles per hour? It takes about 5 horsepower. So in other words, you're using more horsepower from the engine to make this electricity, this current, to make your hydrogen, than it's taking to roll down the road. You know what? In the same little vehicle, your air conditioning alone might be 10 to 15 horsepower. You know, the air conditioning in a vehicle can be 2 to 3 tons in capacity if you related it to your house. So you think, oh, I got a 200 horsepower engine, or I got a 100 horsepower engine. Well, that's at wide open throttle, pedal to the metal, getting 10 miles a gallon, not 40. Going uphill, pulling a trailer with a headwind and fully loaded with squirrels and nuts. That's your maximum horsepower. Takes about 5 horsepower. How do you know this? Well, it's real easy. It's called a coast down test. You can take your vehicle, you put it on a flat surface of land if you can find one. You get it up to 70 miles per hour. Get up to 75 miles per hour, okay? And get yourself a bunch of stopwatches and a little voice recorder. And at 70 miles per, and take your foot off the gas and put the thing into neutral and start coasting on a straight piece of road with no wind, no uphill, no downhill, perfectly level. 70 miles per hour, hit your stopwatch and record the time. Time 0. At 60 miles per hour, record the time. At 50 miles per hour, record the time. At 40 miles per hour, record the time. At 30 miles per hour, record the time. At 20 miles per hour, record the time. At 10 miles per hour, record the time. Now, you know the mass of the vehicle, okay, which is the weight divided by the gravitational constant. Now, you know how long it took you in seconds to go from 70 to 60, from 60 to 50. This is called time rate of change. What's time rate of change? It's called acceleration. There's a little formula you should know that you should know better than E equals mc squared, and that formula you better know is force equals mass times acceleration. It's actually a small a. F equals ma. So since we know the mass of the vehicle, we know the acceleration, time rate of change, thus we know the force. What is this force? This force is equal to, I can't draw a vehicle, it's equal to all of the wind resistance and all of the rolling resistance acting on the vehicle. So you can calculate your force, which is the number of horsepower it takes your vehicle to go down the road. In a small, efficient vehicle, it'll be 4 or 5 horsepower. Sport utility vehicle can be 10 to 15 horsepower. So that's a little side here. If you don't believe me, it takes 5 horsepower to make a vehicle go on the road. You can do the calculations yourself. If you don't know how to do this, and I'm not going to explain it, then that is exactly why we should be graduating more engineers today, who should be studying more physics, more mathematics, and more chemistry. But just for a side here, that's how you get the 5 horsepower number. That's how you can calculate how much energy it takes for you to go down the road. So anyways, we got ahead of ourselves a little bit. Okay, 7.9 horsepower. We are going to come back and we're going to take this number right here. 4,400 watts is needed, which was 13.8 times 320, to get our 5% H2. So we're going over here. We have 4,400 watts. Now what did I tell you? 4,400 watts equals how many kilowatts? That equals 4.4 kilowatts. So over 1 hour, 4,400 watt hours equals 4.4 kilowatt hours. 1 kilowatt hour is what? Okay, everyone say it. 3,412 BTUs used up in 1 hour. So, 4.4 times 3,412 equals 4.4 times 3,412 is, we need, that is 15,000, it's 15,012 BTUs, which we will round off. We need 15,000 BTUs of work from the engine. Okay? Now, your internal combustion engine, normally aspirated, homogeneous charge on a good day, all day long, if you're lucky, is going to be, with generous numbers, 22.5% efficient. Now, diesel, this is higher, but we're not talking diesels. 22.5% efficient. What does that mean? To make this 15,000 BTUs of work at the shaft, I am going to need to burn 15,000 divided by 0.225, divided by 22.5%. I'm going to need to burn 66,666. Now there's a thing called significant figures here. So let's just say I need to burn 66,700 BTUs of gasoline. And what did I tell you? I told you there's 120,000 BTUs in 1 gallon. So 120,000 divided by 66,700. Sorry, 66,700 divided by 120,000. I'm a little nervous here on camera. I need, my fingers aren't working. One of my 0 buttons wasn't working. I need to burn 0.55 gallons of fuel. Now, supposedly, we were buying this little electrolyzer plans and things off of eBay or hither and yon to increase my 40 miles per gallon fuel economy to 45 or 50 or who knows whatever. And I ended up burning an extra ½ gallon of fuel, 0.55 gallons of gasoline, to make the 320 amperes that I didn't have from my 120 ampere alternator, so I had to add a bunch of more alternators on my vehicle that didn't have the horsepower to make it. That's with my 60% efficient electrolyzer, not the 10% one, so you can just multiply this number over here by 6 and say I'm not using 0.55, I need an extra 3 gallons of gas. So, but in these generous numbers I just gave everyone, we used an extra ½ gallon of gas to make this hydrogen, to improve our fuel economy, and we burnt 1.5 gallons of gasoline to begin with. Do you see how all of this comes to the mathematical conclusion that I drew earlier, that these underhood electrolyzers are 100% BS? So in no uncertain terms will this video talking about the science of hydrogen being added to a vehicle in 5 to 7% to do hydro boosting, to improve your fuel economy, to run not homogeneous but stratified charge, which Roy covers, and a non-aspirated engine, which means on an unthrottled engine, the throttle's gone. So don't think you're going to take what we're talking about here and go buy one of these electrolysis kits and put it underneath your hood, get the same result, because you're not. You're going to have a tank of hydrogen on board or something with similar characteristics, because you're not going to do it with electrolysis. And again, I'm going to show you for emphasis what the end result of all this mathematics boils down to. You got it? Don't do it. Don't waste your time. Stick with the science.